just in my buffering stage. So Dr. will just give us a minute and we'll leave it till start. Yes. Welcome everyone back in the next session of the day. And now we have Dr. Govind Umarji. He's a scientist at CMET. And Dr. Govind received his PhD in Electronic Sciences from the Department of Electronic Science, Pune University. And he's working as a scientist at Materials for Renewable Energy and Sensor Division, CMET Pune. Recently, he worked for electronics technology. Recently he worked as postdoctoral research professor under Brain Korea program at the School of Mechanical Engineering at Sungkyuan University. Am I right, Dr. Govind? How do you pronounce it?
Sungkyuan University. That's right.
Yeah.
In short, it's called SKKU.
Okay. SKKU University, South Korea. He has more than 10 years of research experience in the area of nanomaterials, based applications for optical, chemical, temperature sensor applications, solar cells, etc. So now we'll be having a very interesting session, and I would request our participants to have a similar interactive session like we had with Dr. Aman Edward, so that the momentum for the nanosciences continues for the day. Over to you, Dr. Govind.
Thank you, Swapnil, and thank you, Dr. Somnath, for giving me this opportunity for presenting my work and for kind introduction. So let me share my slides. Entire screen. This one. Okay, are my slides visible?
Just a few seconds, sir. Yes, now they are. You can just go into full screen mode.
Yes. Are they fine now?
So we are seeing your screen as a presenter. So we have both the screens. You can just put it in full screen mode.
Is that fine now?
No, sir, we are seeing like your two screens, which is for the presenter.
I don't know.
So maybe you can just instead of having
Okay.
Yes, thank you so much. Yes.
Okay.
Please go ahead, sir.
Yeah. The topic what I have selected in this case is photopatternable nanocomposite for sustainable development of high density electronics and sensor application. See, any development required two aspects. One is a scientific goal, that is one of the aspect, and another is technological goal. So one application as a technological goal, Dr. Amayakar sir already discussed about that, already presented. I will show one more application of this. Before starting that application, I will give a scientific goal, what is theory behind this photopatternable nanocomposite. So the outline of this presentation will begin with introduction. What is trend in hybrid microelectronics technology, then technology for use for this hybrid interconnections, conventional HMCs, then why the photopatternable comes into the picture. So then what are these based? Typical process schematic, development prerequisite, material aspect. Then some of the study on the commercial phase. See, some of the slides may be overlapping with the previous presentation, but I will give a little bit more information on that. Then real part comes with the scientific goal. In that goal, any development, we need to optimize certain parameters to make it at a technological level. So we optimize its synthesis and material characterization by various ingredients like functional material, glass binder, organics, then their characterization. In second part, we have to aspect two major we have to optimize two major aspects. One is its organic solid content, and second is its inorganic permanent binder, that's glass. Then there are physicochemical characterization like SEM, TG, XPS, AFM. Each have their own advantage to understand this. Then electrical properties, sheet resistance, shrinkage properties, then concluding. Then the comes technological goal. In this technological goal, already Dr. Amayka sir discussed about the microphoto patterning of microphotoconductor. That part I will not complete it. That part, just a moment. बंद करायला. And the second part, one more part I will, as a technological goal, I will explain a photopatternable micro thermistor fabrication using this photopatterning technique. So what are the trend in hybrid microelectronics? See, the current microelectronics needs to be decreasing feature size, yes, then increasing scale of integration with less material need to be used, and which outcome will be the greater speed, high performance, which is at something at lower cost. That is what something required, something more required in something less. That is the current trend in the hybrid microelectronics. So, which are the technologies used for these interconnections? Traditionally, there are three major technologies which are played for interconnection. Interconnection is required, plays a role where your chip to real world, we have to connect it. So how to connect it? We require some interconnections. So for that, there is a thin film technology is there, thick film technology is there, multi-chip module is there, where we have to stack on one another to make a 3D structure. So multi-chip modules are there. So all these have their own advantage and disadvantage depending upon their application. So what are the properties which decide which technology we have to use it? So generally thin film technology, yes, it has advantage when we required application in high frequency application, high density application, high tolerance, low noise, where thick film lacks. They don't have, we have little advantage on that. Where the application where we require power dissipation, encapsulation, resistivity range, the development and turnover, that is also one important parameter where the thin film we cannot proceed at that level of industrialization. Where thick film, yes, it can go. In terms of the reliability, reproducibility, and design flexibility, both technologies are at same level. They are proven. But when it comes to the quantity and the capital outlay, uh, the real advantage of thick film comes into the picture. And quality wise, both technologies are good. So these are the major part where we have to consider which application we have to go, we have to use it. So generally, thick film technologies and conventional HMCs, where hybrid microcircuits I'm saying as HMCs, where thick film technology is used, where it is used by a standard print dry fire process on 96% aluminum. There are various compositions, nano composites. We generally in terms of we say as a paste, which are in the form of conductor, dielectric, resistors are available. Lower cost as compared to monolithic ICs, but higher than PCBs. They are the moderate in between the PCBs and the ICs. That's why we require interconnections. Then it's provide substantial reduction in the size and weight with the improved reliability compared to the circuits made on PCBs. But it's not good enough for the present day packaging because we need to reduce the size of the electronic circuits. Again, there is a limitations that we cannot produce line and space dimension less than 250 micron in the production line. That is the real challenge of the thick film technology. Then it has a difficulty to have fabricate a buried layer or buried resistor in the electronic circuits. Application limited to the replacement of the conventional circuit, limited to in interconnection of high pin count. See, if you have chip having more connections, then the pin count has a limitations, because we have limited line and space, limitation in the line and space. Then of course it has a limited high frequency range, like less than 50 for more than 50 megahertz frequency. So these are the technologies which are limiting the thick film technology. Thin film produces, but it has uh, we can say that very highly energy intensive and cumbersome technologies. So why we require photo patterning thick film technology? Yes, this require photo patterning because it has an excellent electrical properties. Special geometrical resolution that is less than 100 micron, quite comparable to this thin film technologies, and energy, because these are the high cost equipments we require for thin film technologies. Then energy is required, turbo pump is required. So this is cannot be possible using standard thick film technology. Then this photopanorama technology gives good edge definition, relatively smooth surface. Because of this special photo patterning, we can go relatively high density interconnections, low cost. Yes, because thick film technology not required much more instruments or much more mechanical parts. So it is a relatively low cost with the proven reliability and the production capability, where our industry can afford it. General industry kind of. And the last one is the environment friendly processes. Thin film technology, they are the good, but they uses chemical to develop each out, and so they are not that much environment friendly as compared to the thick film technology, or in this case what photopatterning technology is that. So what are this photopatterning technology? See, there are two core technologies, as I said before: print, dry, and fire. And the conventional thin film technology use this process, like we have to deposit the material by your vacuum evaporation or sputtering. Then you have to spin coat the photoresist, expose, and then chemically develop it. Then after development, we have to etch the metal, then strip the photoresist. So there are a lot of cumbersome processes are involved in this case. And what we are planning in the photo patternable technology is that we are just adding one step in between the conventional, that is exposed and developed by aqueous developer. So what we will get, we can overcome the limitations of the traditional thick film technology by taking advantage of the thin film technology processes. So it's typical process look like is that first you have an alumina substrate. Over that, you screen print entire area by your photopatternable thick film paste. Then exposed through a UV light using a photo mask, where the part get exposed, get shrink up, get cross linked up, and after that we have to use aqueous developer to develop unexposed part, which result into selectively patterned structure, and then fire at standard thick film firing process. That conventional firing furnace is uh, useful for this, so we don't require any special kind of firing furnace. So to develop such kind of uh, nanocomposite, we required special kind of prerequisites, because it's not a single area; it covers multiple technologies. Like to develop a paste kind of thing, we require to know a formulation technology, then a particle technology, that's metallurgy required because the functional material is there. Then we need chemistry and physics of we need to know that chemistry and physics of your organic and polymer system. And third one is rheology. Rheology is required to know the viscosity of your nanocomposite, which is required for that. So based on these prerequisites, one can develop such kind of technology. So it's not like that that these technologies are not available in the recent market. There are few companies in the worldwide. They have monopolies of these composites, like DuPont, then Hybridos, uh, Herois, but they have their own monopoly. And see, for country like in India, we have to have some strategic developments are going at. Strategic sectors, they require this, like such our space applications. Um, they required these kind of pests. So they demanded for development of such kind of pest nano composite composition. But they have specifically said that we require exactly same properties what commercially, because already they are using those composite for their current application. And if we said no, we will give better than that, but still they resist, yes, that's good, but we want similar properties. So in order to demand such requirement for their strategic application, we need to study first what these commercial nanocomposites are based on that. So we studied by taking an example of silver nanocomposite, and we reverse engineering that by and we took scanning electron microscope, where we found that the particles are in the range of say 100 to 200 nanometer maximum. Some of they are in the range of 2 to 3 nanometer, in the range of 300 nanometers. But if we see the composition wise, the EDAX is clearly shows that the composite is consists of silver, lead, then silica, and some of the ingredients they purposefully mask so that people will not understood that. That part is really tricky part. We have to understand that. And then after, one more study is required from the decomposition of this organic content. After we have to study thermogravitic analysis, where we can find out how much at what temperature your this nanocomposite organic get decomposed. So these commercial paste get decomposed. What is the decomposition rate, steps? Two, is it a single step, multi steps? That we can understand. In this case, what we observe is that this is at around 500 degrees Celsius. The organic should get burned off, and the organic to inorganic ratio, how much they are using it, approximately we get an idea that they have this ratio of 60 40 70 30 they are using for this composition. So TGDTA we have done. Microstructure, in order to get electrical properties, performances, we need to know the microstructure of that, how the grains are getting attached with each other. So we study that microstructure. We got to know that they are closely bound with each other, having some kind of pinholes. These are the fired microstructure of that film at 850 degrees Celsius. So after that basic understanding of that commercial paste composition, we start our scientific goal by proposing our methodology. So in this case, we define our photopatternable composite by taking four major ingredients. One is your functional material, that is either silver, gold, or like in the previous case, Dr. Amayakar sir told about that CDS. Those kind of are the functional material. Then we need to have a polymeric binder. That polymeric binder need to make a nanocomposite which bring that photopatternability. So that polymer binder is required. Then we required a photo initiator. That photo initiator get initiated, that initiate its free radical polymerization at particular wavelength and get cross-link that polymer. And third and fourth one is your glass binder. Glass binder also plays an important role to adhere your film with the substrate. If there is no adhesion, there will no substrate, and ultimately it affects the performance of your ultimately hybrid microcircuits. So once all these ingredients we mix thoroughly, then the formulation comes, the rheology comes, rheology technology comes into the picture. We have to adjust the viscosity to get ultimately printable form. Then after that rheology we achieved, we need to screen print, then expose through UV light of desired through desired pattern, then develop with aqueous developable solution. See, it need not create the toxicity or environmental issues. So the development need to be aqueous, and then it need to be fired at standard firing cycle where thick film technology is used to fire at 850 degrees Celsius. So in this case, we also have to fire with standard protocol. So I'm taking an example as in silver as a functional material. So in this case, we have prepared silver powder using a controlled chemical reaction technique. It's a chemical reaction technique where silver nitrate is used as a source for silver, hydrogen hydrate used as a reducing agent, and in order to have the morphology or uniform dispersibility, we have to add some we have to add some surfactant to cap the those nanoparticles. In this case, we use octanic acid and triethylamine to have dispersibility as well as capping agent for that nanoparticle. So we need after once we selected this precursor, we need to optimize this process in order to provide as per industry standards. So which are the parameters we have to give this parameter to the any industry? So we need to optimize first. So which are the parameters we have optimized in this case? We optimize reaction temperature, then the reducing agent drop rate, that also controls the morphology and the grain particle size of your nanoparticle. Then the stirring rate also, what we observed that uh, need to be optimized and find out the exact solution, exact rate. So after varying these parameters, these are the various morphologies what we observe. So in this scanning electron microscopy, figure A and B are the images which were observed at when we keep the drop rate at 25 to 28 drops per minute, and the stirring rate at 550 rpm. And the figure C and D shows we have maintained the drop rate but reducing the stirring rate. What we observed is that there is a complete uh, bigger size of the particle were observed. The particle size got increased if you reduce the particle size. In this, another set of experiment, what we have done is that we have increased the drop rate, reducing drop rate, and RPM to 650, the motor speed of 650 RPM. In this case, we got particle size, but fine particle size. But in this case, what we observed that particles are diffused, and there are various size and shapes are also observed. In this case, if you increase the motor RPM. In the third case, what we have done is that we have uh, reduced the bath temperature and as well as maintaining the RPM of the motor. And what we observed is that we got the monodispersed particle size, which are in the range of 200 to 300, 200 to 400 nanometers. And lastly, what we have observed is that if we introduce a sonication in between during the motor RPM, that will give more dispersed and uniform particle size. And in the summarize, we can say that if you, the particles are the silver powder synthesized with reaction temperature of 18 to 20 degrees Celsius with reducing with the reducing agent drop rate of 18 to 20. With stirring rate of 550, with ultrasonication, we got uniform spherical monodispersed particle size in the range of 200 to 300 nanometer. The color, the physical properties also says a lot of things, like color also define how much the particles, silver powders, is quality of the silver powder. So once the silver powder is optimized, we come towards the polymeric binder. See, polymeric binder plays an vital role or important role in the photopatternable paste composition, because it need to be attribute aqueous developability and resolution of the final resolution of the resultant pattern. So after a long study of around 6 months, we have to need to optimize the protocol and various catalyst and basic ingredient. We got to know that we need to synthesize this polymer in 2 steps. What are the ingredients we took it for that? We took Novalep epoxy resin. See, there are various kind of epoxy resins out there. Out of that, after that, what we understood that Novolec epoxy has better adhesion with the substrate. It has a good thermal stability also. And considering that, we selected this Novolec epoxy and we reacted and modified with the acrylic acid to have a cross-linking group to that functional Novolec epoxy in the presence of catalyst. So this is the setup what we have used for the synthesis. And in that case, we have second step we added after that reaction. Tetrahydrophthalic unheaded group is again modified, reacted with epoxy acrylate in order to have an aqueous developability. So each and every step we have to analyze what kind of whether the reaction is successful or not successful, whether group attached. So we took an FTIR of the base polymer, where it clearly shows that there is a broad range near 32003600 centimeters, which can be attributed to the hydroxyl stretching vibration of the phenolic group because the Novalec resin. Then 2924 centimeter inverse, that is belongs to the CH vibration. Third group is third strong. There is a strong peak at 1244, 1035, 1114, then 1176, which are corresponding to COC stretching group mode of the eternal group. And the third one at 912, which is an characteristic group by characteristic CO bond, which is oxygen group is occurred at that. So we have modified with the acrylic group, and what we observed is there is a strong peak at 11722 centimeter inverse, which is a characteristic group of ester group, and that clearly says that the reaction with acrylic acid is get confirmed. And there is a disappearance of the COC bond in oxygen free, confirms that the acrylic acid is reacted. And then after the second stage, we have reacted this epoxy acrylic with the pendant carboxylic group. We have clearly shows that there is absence of characteristics unhydride carbonyl peak in the range of 18000 to 1850, confirms the completion of this reaction. Once we understand the reaction got complete, we also study the decomposition of this Novalec epoxy. Since the Novalec epoxy is known for its good thermal properties, we studied that for considering our paste formulation. See, we can see that all the organic burns. See, there is a requirement that should burn before the phase transformation of the glass, in order to avoid in order to avoid the embedding of the contamination or the residue in the carbon. See, during the firing process in our main paste composition, we are using glass as a binder. So there is a requirement that our organic should burn before the glass start melting out. Otherwise, what will happen if there is a carbon remaining, your organic is not get burned up, that carbon will get embedded in the glassy matrix of the glass, and which will hamper the overall properties of the composition. So in order to optimize, we have optimized by taking various characterization technique by FTI, then DGDTA. Viscosity also we have done measurement in order to have rheology of property. This is the total structures where we identify which group will give much more properties. Where in order to have cross-linking that properties, these double group, unsaturated group get cross-linked after exposure to UV light. This group will provide aqueous developability, and this is what we propose structure of modified synthesized polymer. One of the easiest way to understand the conformability, or we can say CT test, that self-standing formation of the film. To see that, what we have done is that we took the polymer, simple modified polymer. After that, we added photoinitiator, exposed to UV light, and it need to be have self-standing transparent flexible film. That need to be a characteristic to understand that your organic polymer is ready for the composition. The third part is that we need to find a permanent binder, that is a glass binder, which is important to have adhesion properties with the substrate of any HMC. HMC need to be have good adhesion with the substrate. So in this case, what we got initial idea from the commercial paste that it contained lead and some silicate. So we have decided to synthesize a borosilicate based glass by conventional method. It has people don't know about the conventional method. I will little bit explain about that, how the glass is formed. Particularly, we have to weigh appropriate weight percentage of lead oxide, silicon dioxide, boron trioxide. These are the ingredients which need to be thoroughly mixed in the ball mill. After that, in the planetary ball mill, in presence of some dispersant like acetone and 2-propanol for 12 hours, we have to mix it thoroughly. After that, we have to pre-dry and fire with a specific cycle. What kind of cycle required, I will show in the next slide. Then after that, we have to the admixture we need to melt in the muffle furnace at 1000 degrees Celsius. This homogeneous molten liquid was then suddenly we have to quench it in a cold water. Otherwise, if we didn't quench it, we will get difficulty for making the powder. So that quenching adds brittleness into the for that that binder, and then the related glass feed need to be clear and transparent. Need to ball mill to obtain the powder size in the range of 2 to 5 micron. So how can we define that how much temperature or what is the firing profile required? There are some literature surveys there where we can say that there is a phase diagram of lead oxide, B2O3, and silicon dioxide. Based on that, we have to select the application, and from that application, we have to find out what is the melting glass transition temperature required, and accordingly we have to select the composition of 3 ingredients. In this case, we have selected this ingredient because we need to have glass melting after 550 degrees Celsius, and before the softening of your nano silver powder. So this is a protocol we optimize for synthesizing our glass powder, and at 1000 degrees Celsius we have suddenly quenched this quenched this molten mass. In order to confirm that whether the glass is really formed, one way is that we have to characterize by XRD. So this is the X-ray diffractometer where we can see the lead sulfide, silicon dioxide, then boron trioxide, then L2O3. These are the different precursors have their own XRD pattern, and this is after add mixing all ingredient we took XRD, and after centering, after making mold, after melting and sudden quenching, we took XRD. See, vanishing of the, see, XRD pattern shows that the molten mass is represented at the lower part of the graph, shows none of the initial crystalline powder phase are observed in the fired glass. That confirms that this glass is in first nature. Then after uh, uh, okay, the once glass is ready, we need to find out what is the glass transition temperature. In terms of the glass transition temperature, we have to perform DSC of that material. From that, we can clearly say that the most important parameter is Tg, and it corresponding to the temperature when the glass begin to transform, to sinter, or to adhere with the substrate. So we can deduct from this DSC spectrum that this glass is get softened, melt at 585 degrees Celsius. So once it is crushed within a ball mill, we need to find out what is the size of that glass particle. After initial 32-hour ball mill, we got this particle size, and after 48 hour, we got our particle size in the range of 2 to 3 micron. Again, once this all ingredients are ready, we have to study and optimize the two major aspects of this nanocomposite. One study is that to study the effect of solid content of that organic system in for the paste composition or the nanocomposite, which is used for photopaternal composite. And second is effect of weight percent of your permanent binder, because permanent binder plays important role for the adhesion. So in the first part, what we have done is that we we vary the solid content of the organic system, and by keeping the organic to inorganic ratio of two ratios, that is 42 as to 58 and 28 as to 72, that without taking care of adding some of the solvents, little bit solvent is required to adjust the viscosity, and we now nomenclature it Hg4, Hg6, Hg7, Hg7, Hg8, Hg10. Out of that, after that we have characterize all the samples by SEM EDAX for microstructural and elemental analysis, TGDT for thermal studies, XPS required to see the surface composition of that, what is happening during the exposure, unexposed and developed. Then AFM for topography of your fired and fired film. Then electrical properties is important from the electrical point of view. So to compare it, we took two compositions, that is the SG4 compositions, where solid content is 70% and organic to inorganic ratio is of 42 as to 58. So in this case, what happened when we expose it and develop it, we found a good unfired, unexposed pattern of 100 micron line, with relatively acceptable edge definition in unfired sample. But when we fire it, there is obviously it contain less solid content and organic content in the composition. We got very discontinuous line and space with poor edge definition after a typical firing process. In terms of in the case of SG7, where we have taken the solid content of 89.9%. For comparison, I took two samples, SG4 and SG7, and having organic to inorganic ratio of 28:72, where we found that unfired sample displays better line and space resolution down to the 100 micron line with good edge definition is also observed. And after typical firing process, we got a better continuity uh, uh, and edge definition also written. These are the circle, red circle shows these are the 100 micron line and space resolution. And then after that, we have seen during the development some of the particles get remain as it is, but that part is an optimization part of your development part that will optimize later on. Once the low magnification images we took it, we have to see the microstructure of that. Microstructure in case of SG4 and SG7, in the poor microstructure with the dominance of voids. Look at this. See, obviously, there are a lot of less organic, less solid content with less organic content. We have to get voids, and some vertical growth is also observed. In contrary, what we observe is that the compact microstructure with less number of voids, and there is a horizontal growth is observed in SG7 sample. And once the microstructure is observed, checked, we have to see the thermal analysis of two samples. So what we observed in the first case of SG7, there are there are thermal analysis clearly shows that there is a it is a less thermally stable. Vertical growth with the pinholes is observed because there is a sharp there is a fast degradation of real organic content, then which result into poor edge definition with rough surface. As compared to the SG7 sample, which contain high solid content, the slope of your decomposition took place in a three-step, where slowly get degrade your organic and ultimately result into the ratio of 17 to 32. So one more way to see the how much composition of your organic to inorganic is present, we need to do TGDT analysis. It clearly shows that that what we have designed 28 to 72 ratio, your organic part decompose with the clearly confirm that your organic content 28%. Then, of course, XPS, what we have studied, how the surface get changed with exposed to the UV light, how the cross-linking takes place, that we have studied using XPS analysis. See, CS1 spectra, carbon spectra, clearly we have taken reference binding energy standard at 284.4, and accordingly we have corrected all the spectra. In this case, unexposed sample clearly shows there are three binding energies, where at 284, 286, and 288, where after exposure to UV light, there is one more bonding is observed, that is CAL bonding at 284, which is dominated in case of SG4, obviously, because it contained more organic content as compared to SG4. But the classic 282.4 peak with binding with the alumina substrate is clearly shows. Then when we see the O1 spectra of unexposed and exposed sample, there is a classic CO. After exposure, we got the peak of C carbon, oxygen, and aluminum from alumina bonding is observed. And another classic that Al2O3 peak is also we have seen. So in this case, we have when we fired it, we got a lot of voids also. So XPS scan also shows that the peak from the alumina substrate, where in this SG4, SG7 sample, we got a classic binding of OCAL as well as Al2O3. Interesting feature what we observed is that when we see silver case in the XPS, the all organic clearly mask that silver peak, and we got there is no peak of silver binding, silver or silver metallic silver. When we fired it, all organic burns up. That confirms that organic all gone, and we got. Since the firing took place in air atmosphere, we got Ag oxide, but the metallic binding energy of 367.9 EV is observed. Then aluminum AlAgO3 also binding. The height of these all peak, deconvoluted peak, clearly shows that the how much is since in case of SG4 we got vertical growth, so that we got more metallic Ag as compared to SG7. In SG7 we got AlAg good bonding as well as metallic bonding and silver oxide, which is because of the air we fired in air atmosphere. The surface also get oxidized with little bit. So in an summary from that all, we what we observed is that what we have assigned the possible assignment is there with binding energy. C1 as in unexposed and exposed sample, we got both linking of the C2 CS3 link carboxylic group and phenolic group is also observed. But in case of the SG fired sample, exposed sample, not fired, exposed sample, we got an CAL bonding, which after cross-linking we have observed. This is evidence that the cross-linking took place. Then O1S also, O1S spectra also assigned that COCL bonding and Al2O3 bonding after exposure, and there is no bonding in unexposed or unfired sample, whereas after fire we got AlAg. We have assigned this based on the fingerprinting or XPS database. Now, the atomic force microscopy is used to understand the microstructure, like how we do see in the scanning electron microscopy. We can see the topography of the sample of the film, where in this case we have SG again took SG4 and SG7 as a reference, and we observed Ag to polymer ratio plays an important role in the topographical smoothness of the film. SG4 film displays a uniform surface as compared to SG7 due to the large amount of the polymer, that is 42%, that goes in the paste formulation. And when we see the unexposed unfired sample down with high resolution 5 micron scan rate, what we observe, there are two peak around 3 micron with a distinct approximation of 400 nanometer corresponding to average particle size of the silver particle used during the preparation of the paste. And this particle is seen to be resurfaced on the resurface at the film due to the higher loading of the silver that goes into paste formulation in SG7 sample, where organic to numeric ratio is 28:72. In the exposed and fired sample of two different SG4 and SG7, we see what we have observed in the scanning electron microscope. There is a dominance of the void and unevenly spread silver particle, silver that observed in the SG4 sample, and buildup of an Ag ice line. See, this is the ice line. Iceland at some of the places in both, but in case of the SG7 sample, we have more dense particle size, dense grown of the microstructure, and the maximum height difference confirms that the photopattern thick film thickness is in the range of 8 to 9 micron. And when we see the more magnifying 20 micron scan, what corresponding to the sample, we can see the cross-sectional graphical representation clearly shows at pointer 1 and pointer 2 that the particle grown up to 4 micron. See, at 850 degrees Celsius, our initial silver particle size is in the range of 200 to 300 nanometer. Nanometer. Whereas after sintering process, firing process, the growth of the silver particle takes place up to 4 micron. This phenomena of particle growth post sintering canly and concretely stated here that the growth of the particle takes place during the sintering process. Then we have measured the resistivity of the film. In that case, we have take Van der Pol technique. So Van der Pol technique is used instead of there are various techniques to use the resistivity or the conductivity. Linear probe measurement is also there, but Van der Pol technique is used in order to have the irregular shaped samples. We can measure the conductivity or resistivity of any irregular shape. So what we observed in this case, the remarkable change observed in the sheet resistance as solid content change. Yes, of course, we can see in this graph that your conductivity, or we can say the sheet resistance, is decreases because there is a good particle to particle grain growth is observed after sintering process, and further improvement in the sheet resistance by optimizing the profile. We can optimize the firing profile in order to have better improvement in the sheet resistance. The second part of this optimization is to see to optimize the glass content, which take a part in the composition. So in the first study, what we observed is that 28 to 72 ratio is more optimized, and now we have to find out the what is the glass percentage, because these data not commercially available. The people don't disclose it in the form of paper patents. We have to optimize ourselves. So we have varied the glass weight percent from 0 to 10 weight percent, and nomenclature as 0 to 10, and intermediate samples we have take for analysis. And in that case, we have done scanning electron microscopy and again gone through 100 micron line and space pattern, which the composition containing 0% glass clearly shows that there is no adhesion and poor discontinuity in the line and space pattern, because it doesn't contain any glass, but lines and we can see the line visually. In case of the 4% glass, this the poor structure is also because there is no adhesion, and the 4% glass, what we observe is that we got better line and space resolution with improved edge definition. 4% glass. Then what we found, low magnification line and space pattern, where we got where I have 10% glass, where we found poor edge definition. That poor edge definition is why we got poor edge definition in case of 10 weight percent. We have to understand that, we have to find out. So we have gone through, we have to study the high resolution scanning electron microscope and cross section of that pattern. So what we observed is that in case of 0% glass containing powder, a poor evolution of the microstructure, because there is no glass, there is no the silver nanoparticles cannot float or make a good growth, because there is no motion or movement of molten glass, then vertical growth of Ag particle, and Ag is unable to spread on the substrate due to the absence of glass assisted liquid phase. That's what I'm telling. We required some glass liquid phase to grow and spread the silver. As compared to the 4% glass containing composition, we got denser microstructure with that horizontal growth of silver. And when we see the 10% glass, yes, there is a hazy effect is observed, that is due to the excess of the glass. This situation leads to a better adhesion. Of course, there is a large percentage of the glass is there, but however, there might be the adverse impact on the sheet resistance of the sample. And in order to study how the adhesion took place with the substrate, we studied the cross sectional of that. So in 0% glass, it shows confinement of the Ag at surface only. Without, there is a, see, this area is your alumina substrate and top is your silver. So there is no interlocking mechanism is observed, leading to the poor adhesion of the substrate. When we see in the 4% glass, we can see that penetration of the Ag in the alumina substrate facilitated by the glass, which also give the signal in EDAX that at a particular point we see that Ag and lead is also observed. Then observation supports the Frit bonding mechanism is present in the photopattern. That is, Frit binding mechanism is particularly a trade phenomena in the classical thick film technology. So in this case also, we have to have that kind of mechanism is required for uh, for that mechanism. So we clearly shows that there is a Frit bonding mechanism is also there. There is an interlocking between the silver and the substrate with the help of the glass binding. And in case of the 10% glass, there is a deep penetration of the lead borosilicate glass along with the Ag, and that gives an hazy effect. And it is inferred from EDAX also clearly suggests that there is a much more interaction of the lead plus glass and in the alumina substrate. So this is that much not good situation from the electrical point of view. So we saw the events, what are the thermal events observed during the firing process. So in this case, total organic weight loss up to 530 degrees Celsius is 28%. We have to analyze what kind of how it is behavior. So weight loss up to 530 belongs to is a total is 28%. Out of that, weight loss below 150 degrees Celsius, this corresponds approximately 4.5% is corresponding to mainly what we have some solvents to have some dispersibility. Then weight loss around 150 degrees Celsius to 530 degrees Celsius, that corresponding to your degradation of the photosensitive organic system, and residue above 530 degrees Celsius is around 72%. That is, this is required for to as a parameter for our manufacturers. They require to know this parameter. So this thermal behavior of our photopattern based composition is typically compatible with the standard thick film firing profile, and similar thermal events were also observed for other paste composition also. Then we have again come back to the measurement of conductivity, because in hybrid microelectronics, conductivity also plays a vital role, because they have to transfer the signal and conductivity. So what we observed that as there is no glass, we have some sheet resistance in the 6 to 7, around 6.3 milliohm per square. But as we increase the glass percent, there is a good glass assisted um, the floating of the silver, and after once the glass get cooled, the that silver grown particles, that we can say it's a flex because they get melt, because here we can see 960 degrees Celsius is typical melting of your silver, and at around 850 degrees Celsius it gets softer and get flex like structure. So that's why your particle size from 200 to 300 nanometer grows to some 4 to 5 micron, and as a result it grows have good particle to particle joining, result into better electrical resistance. And of course, if you increase the glass content, your resistance get increased, and that is not good for electrical conductivity point of view. Again, one more study we have to find out what is the shrinkage at what, because glass when the organic burns, glass get also shrink when it comes to the melting and then cooling. So we have to find out what is the optimum value of the glass where we require to have less amount of shrinkage. So in this case, what we observe is that around 3 to 5% of the glass shows at various line and space. These are the 100, 200, 300, 400. These are the line space pattern, and where we can see that around 3 to 5% glass, more precise, uh, that optimum for composition to have least shrinkage over the range of 100 micron to 700 micron. Ultimately, this image you have must seen previously with the Dr. Amanika sir. We got this unfired sample where 50 micron line we photo pattern, and after firing shrinkage also takes place, and 50 micron line gets shrink to 30 micron. So we have to design our ultimately HMC device according to considering the shrinkage also, and as a result, the conventional thick film, this pattern are reproducible at manufacturing level, or at see the conventional thick film technology. We cannot produce less than 250 micron in production line, where we can consistently reproduce such a dimension in photo pattern technology in a production line. So that's an advantage of this photo patternable thick film technology, by taking silver as an example for conductor. So second part comes where already Microsoft as an application, as a technological goal, how this sustain for the technology. Microsoft already discussed and presented the example of cadmium sulfide. So I will give some another application as a technological goal for this photo patterning technique for thermistor application. Thermistors, as we know that, is a thermally sensitive resistor, and it basically work on a hopping mechanism, and known to have very fast sensitive sensor as compared to your thermocouple or thermocouple, and there are one more technique is that optical technique, where the sensitivity of this thermistor known to have very high. So we thought, why not we use this photo patterning technique to reduce the size of the thermistor, because conventional thermistors are in the range are much more better, much more bigger size, and where the application is required. So where we can use this kind of application, we can use this application on your hybrid microcircuits, Like most of the time we can see our mobile get heat up because of the battery malfunction or the things, or high processing of your software. It gives indication your mobile get hang up, or give indication it will shut down because of your temperature. So there we can use this kind of thermistor. They are using this kind of thermistor for that application. One more application, when we started thinking using this photo patterning technique for that, is that use this thermistor in our turbines, gas turbines, where the fuel and air ratio comes, there the temperature goes up to 1000 degrees Celsius or more than that, and the flames which are moving at that, we have to control the efficiency of that fuel and other things, and that temperature defines how to control it. So we can use this thermistor or on the blade of that fan, where was the initial thought for using this technology, and we decide to develop two kind of thermistors. One is to for high temperature application, that is more than 500 degrees Celsius, and another is for low temperature application. But see, thermistors are typically what commercially available is maximum working up to 300 degrees Celsius, 250 degrees Celsius, not more than 300 degrees Celsius thermistors are readily, easily available in the market. So in this work, what we plan, we done some literature survey and find out around 6-7 protocol to develop low temperature sensors as well as thermistors. High temperature thermistors are not available in the market. So this is an innovative part for us to develop thermistors for high temperature application. And of course, there are very less literature available for this kind of thermistors. So we define around 7 protocol for low temperature application. We have used copper ferrite and manganese ferrite, and in this case, high temperature we use bismuth doped barium titanate, yttria based composite, calcium zirconate, yttria, and YCrMnO3. These are little bit literature available where these can sustain at high temperature with some resistance value. And also we took as a pure yttrium oxide to see what is the effect. These synthesis we took place by various techniques like solid state, co-precipitation, and Sol-Gel technique. In the case of copper ferrite, we use co-precipitation technique by taking precursor from, as a precursor as a copper nitrate, then ferric nitrate as a precursor. We have reduced with 4 molar sodium hydroxide, then precipitation at the heating takes place, then at 90 degrees Celsius result into precipitation of the form, and after that we washed and sintered at 800 degrees Celsius. We confirm after sintering that process, we got that tetragonal structure of copper ferrite, and we matched with the JCPDS data. Similarly, we took copper ferrite TGDTA, where we found that the material is not stable up to 500 degrees Celsius. It needs to be stable. At least it is degrading. That means it's not stable. So we again one protocol we followed, that amine based ferrite. That in that case we took manganese acetate as a source for amine, and ferrite nitrate, and we protocol again citrate acetate is a co-precipitation technique. We confirm that we got the cubic structure of this, and we confirm with the JCPDS data. In this case, we got much more stable. It get oxidized, and then after that, for a high temperature sensor application, we we have tabulated bismuth doped barium titanate, by solid-solid reaction technique, taking this protocol, by taking all solid-solid reaction mixed thoroughly, then sintered at high temperature around 1600 degrees Celsius. We found that there is a diffraction peak, and the intensity of X-ray shows cubic structure of the barium titanate, which is well matching with the JCPDS data. Then we also see the TG, another yttria-based composition also we synthesized by Sol-Gel technique, and then we see the XRD, a high intensity peak, broad peak corresponding to the cubic phase of which was well matching with the JCPDS data, and then the smallest slide size is also observed is 3 nanometer. One more is calcium zirconate, also we synthesize in the same way, solid route technique. We have seen the XRD. Some of the peak got matched with the cubic phase of yttria, but low intensity peak we cannot match because calcium zircon. We cannot understand that it's whether we have to ascribe to calcium zirconate or because there is no data basis available. Now all material got synthesized. The real part comes to have uh, technological goal. So for that we have to process the parameter. The process flow is like that: formulation of the silver paste, what we have done in the photopatternable paste composition. Then screen print on aluminum substrate, fabricate the electrode. Once the electrode gets fabricated, we have to formulate the thermistor paste composition using the synthesized material. Then screen print on a pre-patterned silver electrode, selectively on that gap, and then we have to measure the temperature dependent properties. So this is what we follow the process flow chart. Then we need to have some schematic for the device. So this is a green color, shows we have electrode and the sensing element, that is thermistor material. We have to photo pattern on the gap in between the gap of these two electrodes. So we vary from 100 micron to 200, 300 micron, and we study. We have to study that the temperature dependent property. So to measure this, we need to customize a setup, because when we have to give to some industry, we have to first test at our site. We have customized the setup for that. So we have customized, we have computer-based data acquisition system, and our sample need to be put in the furnace. So for the two kind of sensor, we have proposed this schematic. And then paste formulation, like previously what we have done, silver paste composition, we have followed photo pattern paste composition. Now in the second case, thermistor photo patterning, we have to just replace Ag by our ferrite material for low temperature, and for high temperature thermistor we have to use the high temperature material. So this is the initial test pattern what we have used to pattern our thermistor. And on aluminum substrate, what we have observed is that we got the difficulty to measure to contact, because the contacts are very near. We thought that we have to make first a small device, but the initial attempt was gone wrong. So what we have done, we have again redesigned our pattern, and with elongated contact lengths, contact pad, and these are, first one is I think we cannot visualize because it's a silver on an alumina substrate, but in the second image you can see that we have printed your ferrite material on the gap in between the two electrode, and here is high temperature material which has the gap. In this case we have maintained 100 micron, 200 micron and 300 micron, so as to have compare between which is the best optimized thermistor we can fabricate using this technique. So number of pattern we printed, tested. See, in one case, what we observed is that, as I told you in previous, that glass also plays an important role. We want to measure second part of our sensor for high temperature application, letting more than 500 degrees Celsius. And our synthesized glass has a TG of 670 degrees Celsius. So what we thought, can we use this quartz, because quartz is having high temperature softening in the silver paste, and so we fabricate pattern for high temperature sensor application using quartz glass. And when we started our measurement, we understood in a TG that copper based ferrite is unstable. There is a stability issue. So we focused our main work on manganese based ferrite, and this is the actual initial setup what we have used. This is a temperature sensor to record the data. And this is an electrode, and this is a heating plate, and there is this is a data acquisition system which is connected to computer for low temperature measurement system. And this is a nomenclature what we have used in this case. In order to optimize the glass percentage, we have start with 8% glass and 12% glass, because we need to have high resistance, because this is a thermistor. If it is as the initial resistance is less, we cannot see the temperature dependent behavior. So we start with the 8% and 12% glasses. And here 100, 200, 300, 100, 200, 300, 100, like 3 set of experiment we have done in a single substrate. And we started measuring the resistance versus temperature glass measurement for MN-based glass containing 8% glass. Similarly, we have done for 12% glass. We also check the reproducibility, how it is reproducible. We start with the reproducibility study. The sensor connected to 4, 7, 10 corresponding to 100 micron with 8% glass. What we observed is that delta T is a plus minus 4 degree. And at measured, this measurement were done at 75 degrees Celsius, and resistance is 28 mega ohm for 100 micron line, 100 micron thermistor. When we gone to 200 micron thermistor, we observed is that delta T is 2 degree, delta T is 2 degree, and resistance at 75 degrees Celsius is 64 mega ohm. That is obviously because we have increased the gap between the two electrodes. In third case, what we have done is 300 micron gap, where we observe delta T is around plus minus 10 degrees Celsius, which is not good as compared to this. And at 75 degrees Celsius, we got 70 mega ohm resistance. So in case of reproducibility for 12% glass, again we follow the same process. For 100 micron, we got plus minus 7.2 degree delta T, and resistance is 24 mega ohm at 75 degrees Celsius. Then delta T is for 200 micron 3.7. I will summarize this at the end. I want to show that we have done reproducibility for 100, 200, and 300 micron line with 8 and 12% glass. Because until and unless we do all those data, we cannot conclude what kind of dimension we can use for final production. In case of thermal repeatability, of course, repeatability also takes. We want to see. We have 3 sample reproducible, how much it is reproducible, and repeatability is single sample. We have to do again and again the same measurement and see how much repeatability is there. So in terms of 8% glass containing 100 micron line, repeatability what we is observed plus minus 11 degrees Celsius. Same sample we have tested for 3 times. For 200 micron, we got plus minus 6 degree. For 300 micron, we got 2.24% repeatability. So this is for 8% class. Similarly, for repeatability for a single sensor, we have checked 3 times in order to optimize the delta t. We have to find out. There are typical parameter we have to define when we develop any thermistor. See, any thermistor data sheet, if we see commercial thermistor data sheet, they define the slope. The slope, we can say resistance ratio of thermistor, which is defined as a ratio of resistance at one temperature to the resistance at a second temperature and higher temperature. The slope or the resistance ratio provide an introduction to the concept of change in resistance with the temperature and the sensitivity of the resistance of temperature of the thermistor to the temperature. So in this case, what we observe is that we find out the slope, and it need to be constant or need to be similar in the range. So what 100, 200, 300 micron gap, we found the slope around 13.25, 11.15, quite near to each other. However, in 12% glass, what we observe is that in the range of 75 to 150 degrees Celsius, slope is around in the range of 8.65 or 8.6766. So this is one important parameter we have to define in our data sheet. Similarly, the beta value, we have to define it. What is the beta value of our material or our thermistor? Because it is common practice to specify this thermistor material in terms of beta value over the particular temperature range. So in this case, what we have defined beta value is which comes in the range of 5000 K, and for 12% glass, we got the beta value in the range of 4,000 or 4,200 something range. So this also need to be, we have to mention in the data sheet. The alpha or TCR, that is the temperature coefficient of the sensor, which is the change in the resistance change with the temperature. That the temperature coefficient of resistance or TCR is one of the main characteristics of the resistor. The TCR defines the change in the resistance as a function of temperature. So what we observe is that in this case, resistance, initial resistance at 75 degrees Celsius for 100 micron, and we take final temperature as 175 degrees Celsius to find out. We got TCR values around same in the range of -9.61. In both the cases, TCR remain in the same range. So we modeled this based on that value. We have done some modeling by taking Steinhardt equation. See, in order to have some protocol prototype, we need to have some ABC values given to the microcontroller. How much what we are measured and how the calculated value, we took 3 values, resistance value for that from this graph, one at initial 75, 150, 450, and put that value in the equation, Steinhardt equation. In this case, what we use the temperature, because we want to have thermistor in the up to 500 degrees Celsius, and so therefore we took 3 values, 75, 250 degrees Celsius, and 450 degrees Celsius. These 3 values we put in a Steinhardt equation, and we have calculated and measured both cases for 100, 200, and 300 micron. What we got is that there is a good approximation to the relationship between T and R for the complete range of the thermistor based on the data we just got from the 3 calibration point, and what we summarize from that is all parameter for 100, 200, and 300 micron. 200 micron pattern shows much more less number, less delta T between the actual and model temperature range, and it has much more reproducibility and repeatability also is observed. So we optimize that if we use photo patterning technique for this. The thermistor have to have 200 micron line or of dimension. So once we found that, we modified our prototype in order to have final product. So this is a silver pattern with alumina substrate printed, and these are the three drilled electrode where we can put our bring out the interconnection to the controller, and these are the printed sensing material on that electrode. So single sensor contain a single substrate contain two sensor, and we now much more calibrated, we can say much more advanced data acquisition system what we have used in this case. We have customized to get more precise data in order to have a better data sheet, and accordingly we have measured one the meter measure the temperature, another meter measure the resistance based on the variation in the temperature. And these are the two graphs what we have taken from the data acquisition system. The first graph shows there is a linear change in the temperature, and in this case thermistor shows non-linear behavior. And from the device or the prototype point of view, the value required not in terms of the resistance, they required in terms of the voltage to give this data to any controller, Arduino, or program. So we have measured this value in terms of voltage, and some of people will say, oh, this gets saturated at high temperature, but when we zoom it in that particular range, we found it's not saturated, it's changing the resistance value. And based on that, we again measure its response time. The top side is room temperature. We measure the response at 350 degrees Celsius, starting from room temperature. And what we observe is that this thermistor is responsive approximately 31 seconds. At within 30 seconds, it shows the response time of this thermistor. So once the thermistor prototype is ready, we need to have calibrate this data and need to be have calibrated. So what we found in one Yog Electroprocess private company, where this is an NABL accredited lab, where we have to calibrate it. That they have 25 years of experience in thermal calibration. So we took our sensor to there. They prepare according to their standard. The sensor is here, where our actual sensor is kept inside this, because there is a standard protocol to have calibrate this sensor. So what we observe in both the cases, up cycle and down cycle, the resistance, or we can say that resistance with set value, standard value, and measured resistance value at 75 degrees Celsius and up to 450 degrees Celsius in upward and downward cycle remain approximately same. That means our sensor behave like a calibrated sensors. So from that value, we can take the Stein-Hardt equation 3-point calibration point and give this value to a microcontroller. So this part comes up to 500 degrees Celsius. Now the next part is up to we have to use for high temperature application, which nobody. I mean, there is the less literature available. So that's an innovative part for us. We want to try this for using photosensitive technique. We have followed this protocol, and started measuring the setup. We have customized this furnace. This furnace is and this data acquisition system. We start taking measurement from this and measure. The sensor is connected here with the platinum wire, since we have to measure 1000 degrees Celsius. Again, in this case, what we observe is that silver melt at 960 degrees Celsius. So silver cannot be used for high temperature measurement. So we bought a platinum paste, we printed the electrode, and accordingly we have this sample where the ferrite, I mean the high temperature material is printed, sensing will deposited, and we started measuring. What we observed in this case, uh, when we actually started, the thermistor start getting saturated below 500 degrees Celsius. That means we cannot get highly resistive material to begin with sensing, begin the sensing from 500 to 1000 degrees Celsius. That's why what we thought, the composition or the value weight percent of the functional material is very less. So we started to have alternative. We prepare a rectangular pellet of this different materials having platinum electrode. Start now from here photo patterning technique had some limitations. We understood that, and then after preparing the pellet kind of shape things, we also found that yes, it shows, but there is stability is very poor, contact is very poor. So we have again rethink on that. We started preparing standard size pelletizer, but when connecting the electrode, we found that the repairability is issue. Repairability is the common issue for that, because each and every time electrode has a different location, but it shows sensing properly. With starting resistance, it start from 400 mega ohm at 500 degrees Celsius and reduces to some kilo ohms at 1000 degrees Celsius. But that idea got work. So we fabricate our pelletizer in a such a way that we can embed the platinum electrode inside during the pelletizing the process. And then we check the microstructure, then connection of the platinum wire with the embedded thermistor material, and ultimately what we come with this pellet of 10 diameter and to around 1.5 thickness, and we started measuring and calibrating this sensor. This is a typical profile of a temperature profile of a furnace, where it shows linear increase in the increase in the uh, temperature, and beside that there is a actual sensor measurement, high temperature sensor measurement over the range of 500 to 1000 degrees Celsius. So in this case, what we observe is that this is a yttrium doped zirconia material, and there is a large variation at the initial, then it got saturated. The change in the resistance is very less, from around 800 degrees Celsius to 1000 degrees Celsius. So we saw the repeatability of this, and we observed that it shows repeatability of delta T repairability of 12.5 plus minus 12.5 degrees Celsius, and temperature at 650 degrees Celsius we got R value of 40 mega ohm, and we again modeled it using again Stein Hart equation by taking three temperature range ABC value, calibration point, and we modeled it. We observed that it is quite correlating, but there is a variation in the actual value and the measured value using this three constant. Then we again checked back why this is happening, and what we observe is that there is a very at the initial temperature level, initial temperature range, there is a variation in the resistance, and that gives a wrong value at for A, B, C. We again measure the response time. Response time of this sensor, what we observe is that around the range of 1 minute, which is quite much more slow. Again, then on a sudden, what we thought, one more protocol, we start with that pure yttrium. Why not we try with the pure yttrium oxide? Pure yttrium oxide, when we used it, we found it is much more sensitive, much more better in terms of the stability, in the range of 500 to 1000 degrees Celsius. And we see the repeatability. We got the repeatability range with the delta T of plus minus 8.5 degrees Celsius, and see the range temperature resistance range is 3.47 mega ohm at 750 degrees Celsius. We done this repeatability, reproducibility, and modeling study. What we have got is that ABC value is much more near with three set of experiment. Is much more. That means instead of going other, the pure yttrium oxide pellet is much more reliable. One more thing what we observe is that see this limitation of initial variation. What we are understood why our thermistor behaving like that. We understood that that is not the problem of our thermistor. The problem is behind is because of our furnace and B-type thermocouple. B-type thermocouple is mostly stable above 500 degrees Celsius. That's why the PID is giving this damping structure. And when we saw in detail, what we observed that the material is much more sensitive. That means when there is a change in the temperature, material also changing accordingly. That means thermistor material is perfectly working for this high temperature application. Then we measure the response time of this measurement. What we observe is that at 750 degrees Celsius, response time is 22. And again, we measured it for a different sample, which comes in the range of 22 to 30 seconds. Again, we need to calibrate this sensor. We have calibrated at standard NABL accredited lab, and in this case also we got the value of resistance exactly same when we have gone through up cycle and down cycle in terms of resistance. So from this calibrated point, we can use this value for our microcontroller application, where we have to give this ABC value and Steinhardt equation in the controller during the program. Again, what we have studied, one of the industrial aspect is that it need to be stable for a long duration. So in this case, we start with the industrial, one of the industrial standard, that we have to soak the sensor for 1 hour and see whether the resistance got changed or varied. So at 1000 degrees Celsius continuously soak, we have not observed that much more of change. Plus minus 0.01 degree, plus minus degree variation is observed. That is much more better in terms of the reliability. Then one more aspect what we have think is that what if you reduce, because 10 mm is that much, if you stick this pellet to any blade of any turbine or then how to use it. So we have to reduce the dimension. So we have reduced the dimension from 10 mm to 6 mm, and similar behavior is observed. Of course, much more better is that we got the change resistance. In this case, we start from around 45 mega ohm. In this case, we start with 160 mega ohm. And one of the point is that interconnection. See, one more what we observed is that when we laser solder this platinum electrode with the platinum wire, and done the repeatability study, we got delta T variation is of 5.6 degree. That means it improved the repeatability when we had a proper contact with the electrode. We have again done the measurement in terms of the voltage as per the requirement of the industry by using a potential divider circuit, and again we measured it in terms of voltage. We have done two. In this case, we have done 2 to 3 times. We got exact overlapping behavior, and what we observe is that yttrium zirconia is pure yttrium oxide is much more better than that of yttrium zirconia in terms of the repeatability, beta values, delta T. And we have done one prototyping by using simple Arduino Uno in a program, and I have a video for that to share. If it is, let me show. Uh, uh, in the presentation, it is not working. I will show in this case. So this is the video. What is used for prototype. Is my video is visible?
Yes, it is visible.
Yeah. So here I will start it again. So in this case, this is a actual temperature measured by our thermistor, where this is Arduino, where we have put a program, and these two leads goes inside the furnace where our thermocouple is connected. This is a furnace, and this is the type of the furnace inside furnace temperature. And we have checked, we have demonstrated that the thermistor work at a high temperature properly, and in this case in that way I have completed I have used conventional photo patterning technique for low temperature thermistor application, and for pellet kind of thing for high temperature application, from the sustainability of photo patterning technique for nanocomposite application. One video Dr. Amayka sir told me to show as this photo patterning technique for LDR application, which he cannot play. I will show that also as an technological aspect of this photo patterning nanocomposite open with. Yeah. So this is a counter application using photo patternable photoconductor. This is a chopper, and we apply the frequency here, and this is a counter application. Sensor is connected here. This is a light, and as we increase the frequency, the counting increases. How much we can chop the frequency use as a counter in the industry application, where the LDR is conventionally used for that photodiode is conventionally used for such application, but the photodiode has a limitation that it has a poor signal the range. If I want to measure for a long range for a big product in a counting mechanism, the LDR, the photodiode has a limitation. So we can use this sensor. See, at a higher, very high frequency. Uh, uh, this is a high frequency. Also, this is working very fine. The last digit we cannot visualize it, but we can see that it is counting fast uh, continuously. So LDR, because of the fast high response time, we can use for counting application also. That part was uh, the Dr. America sir cannot show this video because of the compatibility issue at their end. So with this, I like to thank. I think I covered the scientific goal and technological goal in order to sustain the photopatternable nanocomposite in this talk. Now, open for questions.
Thank you, Dr. Govind. The presentation was quite technical for point of us, but nonetheless, it was a good flow that we had. And I request the participants to go ahead and ask some questions that you might have, or if the queries that you considered which could be extended from the previous session to here are also welcome. So, Dr. Govind, I just had a query like,
Yeah, please.
These various materials that have been made, if you can just, in a very generic manner, if you can just highlight where all these can be used for as an end user.
Yeah, yes. One application of CDA photoconductor already Amayaka sir discussed about that. Now about this thermistor application, our most of the industries or even if we see our instruments furnaces where we use temperature sensors, uh, but they are not that much responsive. So there we can, and more advanced application of this high temperature sensors we can use in a jet engine, where efficiency of that engine can be, or degradation of that engine, we can measure it, which part at what temperature the jet engine has a life of the day jet engine. We can uh, calculate from this at each and every point of the point of that engine. So we can use this high temperature sensor for that application also. Thermistors, because thermocouple cannot be used there, because the air dynamics takes place there. If you put well inside that jet engine, that creates thermodynamical air flow imbalance. So if we put or stick this kind of thermistor there, that will help to increase the life of the engine. So that is one of the application or material where we can use this.
Yes, quite an interesting domain for an application. Uh, so far, I have not seen any questions.
Yeah.
Any notes that you would like to add, or any current research that you think our audience should be aware of as to whether these conditions can be fulfilled by maybe by a collaboration or by some other means? It will be wonderful.
Yeah. Now I have given two examples of photo patterning in the application. One more application we can use for another kind of sensor application is that your gas sensor or oxygen sensors. Now, oxygen sensor is nowadays everybody knows that why it is required uh, in this pandemic. Also, oxygen sensor is required for energy application also. Where I was there in SKKU, where the lab is working on solid oxide fuel cell, where the fuels are hydrogen and oxygen, and oxygen need to be precisely go through the fuel cell in order to have high efficiency. So we cannot put thermocouple inside that in that stack or measure it. So what was one of the intention is that use this technology to directly print the oxygen sensor on the fuel cell, and monitor the oxygen while because solid oxide fuel cell work at 550 to 650 degrees Celsius to have high output, high efficiency. So another aspect of this photo patterning we can use in energy related application like fuel cell, where it can be used at high temperature. Thermistors, these thermistors can be used in fuel cell to monitor the actual temperature of that fuel cell. So these are the various advanced applications what we plan or what we can do using these photo patternable nanocomposites. Just we have to change the functional material and find out the properties and measure the properties.
Okay. Wonderful. So, on another note, what do you consider to be a suitable direction where this research is going to go? Like in maybe a decade or so, if you can just share your vision where you think this research will go.
Uh, See, there are a lot of advanced applications are there, but and having traditional see material limitations are there, or technological. I mean, the device problems are there, and because of this technique, we can reduce the dimension. Because of the dimensionality, we cannot use it. In this case, we can use and this technique is more industry oriented, where we do not require high end instrument or characterization technique. We can use it and measure it. So that is the direction we have to take this technology.
Right. And like this program FDP is on sustainability. So, what aspect do you think can be covered? Uh, what component you believe will either reduce the cost or maybe can be recycled, or a recycled material can be used so as to improvise the sustainability concept.
Yeah, of course, that's a good point you said. Any industry wants to have their own standards, and in terms of industrial standard, we can say that, and reliability in terms of see, when I was there. Any device or any sensor need to be checked for at least 100 hours. That is the first industry criteria. And about recycling, since the your sensor material we are using very less amount, uh, uh, one is that material is required is very less. That's one point that our cost get reduced. Another part, silver we can recycle it, functional material we can recycle it, and again reuse it. That is the main advantage of this kind of technique. So the technique need to have this parameter if we want to go to industry level.
Right. Right. So, silver is one such compound that you suggest can be or should be used as a recycled material, right?
Yeah.
Okay, okay, that's good. So, do we have any questions or any audience who would like to have a discussion with him? Yeah, you can just raise your hand and we can go ahead from there.
Yeah, if anyone have questions later on, they can ask. I will put my email address and mobile number. They can directly contact me. I'm near to you. The CMAT is very near to Pune University. We have good contacts, collaboration with Pune University, and they can contact me. They can come to CMAT, visit the facility. There's no issues. Please.
Yes, sir. Thank you so much, Dr. Govind, for saying so. We'll be definitely sharing, with your permission, your presentation. And if you can just add your contact details in the presentation itself, then it will be always available for the participants.
Sure, sure.
Like you and I, we agree that not all the participants will be jumping their current research in this domain, but they may eventually try and look up and you never know how it goes ahead. So then your contact details are readily available. It will be available.
Surely I will provide. Surely. Yeah.
So thank you so much, all the participants, and thank you so much, Dr. Bhuvan. It was a pleasure listening to you, and we hope to have further interactions based on this note.
Yeah. Thank you.
Thank you. The participants will be having a break right now, and will be joining for the third session of the day to be conducted by Dr. Rajendra Patel at 3 o'clock. And he'll be taking the beacon of nanotechnology towards more of a biological applications as well. So please do join us by 2:55 or so, and we'll have the last session of the day then. Thank you so much, and the feedback forms of this session will be following up sometime soon. And if you have any queries, always you can message in the group. Thank you, everyone. Have a good night.